So, as a perspective, right, I mean, let us kind of summarize, right, all the verification techniques that we have seen in this course, right. And what I am going to do, right, is I am also going to mention, right, some of the important properties that we want of verification techniques, right. So, namely soundness, completeness, and whether they are fully automated or not. Okay. So, these are some important properties that we want our verification techniques to satisfy, right. So, in this course, right, I mean, we have seen techniques, which use constraint solvers, right. So, for example, SP, WP and Hoare logic, right. So, they are constraint solver based techniques, right, meaning that they essentially they reduce the verification problem, right, to the constraint solving problem, right, which is finding out whether some formula is satisfiable or not, right. So, you can then rely on SAT solvers and SMT solvers. Okay. And then we have seen this set of techniques at the end, right, which are algorithmic techniques, right. So, these techniques, right, abstract interpretation and model checking as well as CGAR, these are all algorithmic in the sense that they do not rely on any other technique, right, or any other tool, right. So, they are formed, so they have these algorithms, right, which essentially just execute the program, right, in an abstract fashion, right, and are able to verify whether the program is correct or not. Okay. So, in either case, right, I mean, what can we say, right, about these different techniques that we have seen, right. So, let us fill this table. Okay. So, what we have seen during the course, right, is that the constraint solver based techniques, right, which is SP, WP and Hoare logic, these techniques are good in the sense that they are sound and they are also relatively complete, right, meaning that there is a high chance, right, that you will be able to verify programs, you will be able to verify arbitrary specifications, right, of programs. So, remember that program verification does not happen in isolation, right. So, it happens with respect to some specification. So, I can give some arbitrary complex specification and there is a good chance, right, that if you use SP, WP and Hoare logic, either of these three, right, you will be able to actually verify that a program is correct and is able to satisfy some complex specification, right. But the trade off is that these techniques are not fully automated, right, meaning that as a programmer, right, you have to spend more effort, right. So, this more effort is in terms of loop invariance, right. So, as we have seen that I have to annotate, right, loops with loop invariance and only then can I use something like Hoare logic in order to verify a program. Okay. But the flip side is that I can verify arbitrary complex specifications. Okay. On the other hand, right, we have seen abstract interpretation. So, we spent a lot of time on abstract interpretation. Abstract interpretation is fully automated, right, meaning that you do not have to supply, right, any loop invariants, but its flip side is that it is not complete, right, meaning that even if your program is correct, right, abstract interpretation may fail to show that the program is correct, and the reason it may fail to show is because the abstract domain is not precise enough, right. So, if the abstract domain is not powerful enough to capture, right, what it is that you want to capture. So, if you are not able to capture the executions of the program or the specification, right. So, the properties that are required to show that some specification is true, right, then abstract interpretation is going to fail, right. So, in the very first lecture, right, I had mentioned that abstract interpretation is typically used for verifying, right. So, this is static analysis, so it is only used for verifying shallow properties, right. So, shallow properties such as for example, right, that the program does not crash, right, meaning that suppose if you have an array access, right. So, the array access, the indices happen within the bounds of the array, right, those kind of things, right. So, things like constant abstract domain, interval abstract domain, right, they are very good at inferring shallow properties of programs, right, which are just bounds over variables and things like that, right. So, non-relational examples. Okay. So, so that is about abstract interpretation, right. And now, towards the end of the course, right, we have seen model checking based approaches, right. So, for example, we saw concrete and symbolic model checking, right, and these seem to overcome the limitations of the previous two techniques, right, meaning that of course they are sound, right, but they are also fully automated, right. However, these techniques are also not complete, right, meaning that because they run into termination issues, right. So, with concrete and symbolic model checking, these algorithms may never terminate, right. So, even if you have a program that is correct, if you run concrete and symbolic model checking, this algorithms themselves may not terminate, right, because they do exhaustive state space exploration. Okay. Bounded model checking, on the other hand, uh, is able to overcome this termination issue because it is guaranteed to terminate, and it is also complete and fully automated, meaning that if the program is correct, right, if bounded model checking will say, right, that the program is correct, but it is not sound at all, right, because it only explores the state space up to a bound, right, meaning that if the bug lies within the bound, then it will be able to find it, but if it lies outside the bound, right, then it will still say that the program is correct, but the program is not actually correct, right, meaning that so if bounded model checking says that the program is correct, meaning that it has not found any bug, that does not mean that there does not exist any bug, right. So the bug may exist outside the bound that is checked by bounded model checking. Okay. However, they are also fully automated, so bounded model checking is fully automated and it is also complete. Okay. The last technique that we saw, which is CGAR, right, which is probably one of the most advanced techniques in automated program verification, right. So this kind of overcomes, right, the limitations of all the previous 4 techniques, right. So it combines ideas from both deductive and algorithmic program verification, right. So it uses SAT solvers, right, it uses SAT solvers and SMT solvers, right, to check, for example, feasibility of the trace formula, right, and interpolation computation, but it is also algorithmic in nature, right, because it does not rely completely on SAT solvers and SMT solvers, right. So instead it uses those solvers intelligently, right, and it does some algorithmic computation, right. So the CGAR is deductive plus algorithmic, right. So it combines both deductive and algorithmic approaches, and the output, right, the sort of end result is that it is probably the most successful out of all the 5 techniques that we have seen, right. So not only is it sound and fully automated, but again it is also relatively complete, right, relatively meaning that because it restricts the space of predicates, right. So if you want guaranteed termination, then you have to restrict the space of predicates, and therefore if the program can be verified to be correct within the restricted space of predicates, then CGAR is guaranteed to verify such a program. Okay. So using CGAR, CGAR is fast, it is efficient, and it can also verify arbitrarily complex specifications of programs, okay, or at least more complex than those which are verified by abstract interpretation. Okay. Okay. So these are all the techniques that we have seen in the course, right, but this is not this particular slide, right, this is just the starting point, right. So this is not an exhaustive set of all verification techniques that are present in the literature, right. So in fact verification, right, and automated program verification, so this is an area where we continue to see new ideas, right, new results, new techniques, right. So there are lots of other advanced automated verification techniques which we have not seen as part of this course, right. So for example, property directed reachability, right. So this is a new technique, right, which has come up in the last decade, right. So maybe around 2010s, right. This new technique was discovered which overcomes some of the limitations of CGAR as well, right. Then there is constraint horn clauses, which also is a new technique, right, that was discovered in the last decade. And now with the advent of machine learning, right, and data driven technology, right, we are seeing new techniques which are called black box techniques, right, where you learn loop invariants, right, using data, right. So using data driven CHC solvers or ICE learning, right. So again these are new techniques which we have only seen in the last 5 years, right. So these techniques have come up in the last 5 years, and this is a constantly evolving space, right. So verification of course is automated verification is undecidable, right. So you will never have a technique which will always succeed for all programs, but what we really want to do is we want to verify a maximum set of programs, right. So as many programs as we can verify, and not just verify simple properties but complex specifications, right, full functional correctness and so on. Okay. So this is ongoing research in automated verification techniques, but what we have also restricted ourselves in this course, right, is we have only looked at sequential programs, in particular sequential imperative programs, but there are other programming paradigms, right. So there is concurrent and distributed programs, right, multi-threaded programs, GPU programs, right, and there is also functional programs, right. So for this different kinds of programming paradigms, right, we need a new arsenal, right, a new sort of set of techniques, verification techniques, and again there is active research in these areas as well, right, especially for concurrent and distributed systems, right, which are much more complex to reason about than sequential programs. Okay. And of course, I mean, so far we only said about programming paradigms, but what about the safety specifications, right? So what about the correctness properties that you want to verify? Right? So uh, there are new sort of properties, right, that we are interested in: security and privacy, right, meaning that protection against cyber attacks, right. So we are not just interested that the program runs correctly, but we are interested in the fact that the program runs correctly in spite of some adversarial attacks, right, or in spite of someone actively trying to mess with the program, right. So in the presence of such elements, right, in the presence of such elements, is the program still guaranteed to run correctly, right? So these are the concerns about security and privacy, right. And of course there is a whole new paradigm of programs which are machine learning frameworks, right. So here you would be interested in various properties, right, that machine learning frameworks care about. Okay. So these are different specifications, right, for which again you need a new set of verification techniques, right. But so the verification techniques that we have seen as part of this course, right, they form the base layer, right. So all the advanced verification techniques, they kind of build on top of the techniques that we have seen in the course, right. Um, uh, and if you are interested, right, I mean, you can take a look at some of the recent papers, right, in the different verification oriented conferences, right, and you will be able to get a sample, right, of the research that is happening in this area. Okay. Okay. So with that I am going to end this course, right. So this is the conclusion of the course, and this is what we have seen as part of the course, right. So started with constraint solvers, then deductive verification using constraint solvers, and finally some advanced automated techniques. Okay. So with that I end the course. So I thank you for your attention throughout the course, and I hope that you are able to learn something new and interesting. Okay. Thank you.